In the early 19th century, John Dalton proposed a groundbreaking theory. Matter was composed of tiny, indivisible particles called atoms. This elegant idea revolutionized our understanding of chemistry, providing a simple framework to explain chemical reactions and the composition of substances. Dalton's atomic theory suggested that atoms were the smallest possible units of matter, like tiny solid spheres that could not be broken down further. This concept of indivisible atoms became a cornerstone of chemistry for many years. Dalton's model, while groundbreaking, had its limitations. It could not explain certain phenomena observed in the late 19th century, particularly those related to electricity and magnetism. Scientists began to suspect that there might be more to the atom than meets the eye. The discovery of subatomic particles, entities smaller than the atom itself, was a pivotal moment in the history of physics. Among these subatomic particles, the electron holds a special place, being the first to be identified. Its discovery, largely attributed to the ingenious experiments of J.J. Thomson in 1897, irrevocably changed our understanding of the atom and paved the way for modern atomic theory. Thomson's groundbreaking work, conducted using cathode rays, revealed the existence of negatively charged particles that were much smaller than even the smallest atom, hydrogen. This revelation shattered Dalton's idea of indivisible atoms, opening up a whole new realm of subatomic physics. The discovery of the electron began with the study of cathode rays, a mysterious phenomenon observed in vacuum tubes. Scientists had been experimenting with these tubes, known as Crookes tubes or cathode ray tubes, for some time. These tubes, with nearly all the air removed, contained two electrodes, a negatively charged cathode and a positively charged anode. When a high voltage was applied across the electrodes, a glowing beam emanated from the cathode, striking the opposite end of the tube. These were the enigmatic cathode rays. The nature of these rays was hotly debated. Were they waves or particles? Their properties were perplexing. They traveled in straight lines, could cast shadows, and could even cause a paddle wheel to rotate, suggesting they possessed momentum. Intrigued by these enigmatic rays, J.J. Thomson devised a series of elegant experiments to unravel their mysteries. He placed a charged plate near the cathode ray beam. To his astonishment, the beam deflected away from the negatively charged plate and towards the positively charged one. This observation implied that the cathode rays carried a negative electric charge. Thomson then introduced a magnetic field perpendicular to the path of the cathode rays. This caused the beam to deflect, confirming his earlier observation and further strengthening the idea that cathode rays were indeed streams of charged particles. By carefully measuring the degree of deflection caused by both the electric and magnetic fields, Thomson was able to determine the charge-to-mass ratio of these particles. His calculations revealed an astonishing fact. The charge-to-mass ratio of the particles in the cathode rays was significantly larger than that of any known ion. This suggested that these particles were either extraordinarily highly charged or incredibly light, almost 2,000 times lighter than a hydrogen atom, the lightest known element. Thomson's groundbreaking experiments provided compelling evidence that cathode rays were composed of tiny, negatively charged particles, which he named corpuscles. These corpuscles, later renamed electrons, were the first subatomic particles to be discovered. Thomson's discovery of the electron was monumental. It marked a paradigm shift in our understanding of the atom, revealing that it was not an indivisible entity as Dalton had proposed, but rather a complex structure composed of even smaller particles. Thomson's work laid the foundation for modern atomic theory and revolutionized physics. The discovery of the electron, with its incredibly small mass and fundamental unit of negative charge, has had profound implications for various fields. It paved the way for our understanding of electricity, chemical bonding, and the behavior of matter at the atomic level. Further experiments, such as Robert Millikan's oil drop experiment, accurately determined the charge of an electron, solidifying Thomson's findings and cementing the electron's place in the pantheon of fundamental particles.